In the simplest sense, we see because our eyes receive light that's been bouncing around in our world. Our eyes sends a signal to our brain, which interprets the signal and creates an image. Unfortunately, we don't all see things exactly the same way. There are many factors that impact what each of us actually sees. As many as 1 in 12 men experience some degree of color deficiency. Now, that doesn't mean that they see in black and white. It simply means that they don't see colors the same way most people do. At a fundamental level, if everything is working properly, the human eye perceives 3 primary colors of light: red, green, and blue, or RGB. By combining varying amounts of these 3 colors, it's possible to create all of the other colors we see. If you mix red and green, you get yellow. Mix green and blue to get cyan. And mix red and blue to make magenta. Cyan, magenta, and yellow, or CMY. These are the opposite colors, the colors used in most types of ink-on-paper printing. Mixing equal parts CMY produces black, or something awfully dark. This is the K in CMYK. Printing a little bit of black saves printing all this CMY to get the same color. Print no ink and you have white paper or banner vinyl or whatever your media is. And you can get back to RGB by mixing cyan, magenta, and yellow together. Magenta and yellow make red. Cyan and yellow make green. And cyan and magenta make blue. It's important to know these color mixes and opposites, and there's an easy way to remember them. Write RGB and CMY vertically beside each other. The opposite colors fall across from one another. Red is opposite cyan, green is opposite magenta, and blue is opposite yellow. To find the mixes, eliminate the opposite. Here's what I mean. To find which 2 colors make green, eliminate the opposite of green, which leaves behind cyan and yellow. Cyan and yellow make green. Color is also greatly influenced by the other colors around it. Well, that's not true. Actually, our brain is greatly influenced in its perception by the colors around whatever we're looking at. Let me prove this to you. Take a look at this image. In particular, I want you to look at these 2 squares. What colors would you say they are? This one is kind of tan or beige color. And this one is, I don't know, chocolate or dark brown. Now, watch what happens when I mask off the surrounding environment and isolate the 2 colors. The color patches we were comparing are actually identical. But because of their environment, to our brain, they appeared very different. Take a look at this color. What would you call it? How would you describe it? Someone might call it red or brick. Someone else might call it terracotta or even brown. We're all talking about the same color, but we describe it differently. Well, digital devices have that same problem. That's because color is device dependent. Different devices display color differently. If I scan this swatch, the scanner will describe the color with this set of color values. To get my display to create the same color on screen might require these color values. When I send the job to print, my desktop printer will need these color values to get the very same color. That's where profiling and the I1 come in and makes life simple again. By profiling devices, we create a description or fingerprint of how each device displays or captures colors. These descriptions are used in a color-managed workflow to create accurate, predictable color.